Okay, so this is the second video that is talking about enthalpies of formation, and in this video, what I want to show you is how we're going to go about using these enthalpies, these standard enthalpies of formation. So we use these to solve questions such as enthalpy of reaction questions. And before we get started on that, let's just see how we're going to get some data. So we need these tables, thermodynamic properties. In particular, we're after delta HF, kilojoules per mole. And so there's the column for delta HF, kilojoules per mole. And there's another one over here. And so you get a long list of compounds. Now this table isn't the greatest because it doesn't show symbols of state, but again, hopefully you recognize that methane, for example, is a gas under standard conditions, as is, that looks like ethene. I can't really read the small number, but it might be ethene. That's a gas. And then you'll see something like potassium hydroxide is a solid. So you do have to have an appreciation of symbols of states and use the symbols of state. The other thing I do want you to point out is where you have enthalpies of formation is 0. So 0 for Br2. Well, Br2 is a compound, yes, but that's the elemental form of bromine. And so you'll notice the other zeros are for elements. I2, elemental iodine, potassium, elemental potassium, K, aluminum. So elements in their standard state have no enthalpy of formation because they're already in their standard state. So just keep that in mind. That you may have to deal with that in a question. So standard enthalpies of formation are really useful because they provide a convenient means of applying Hess's law, and so it saves us from having to manipulate these thermochemical equations. The Hess's law of heat summation is where we did that. So we have 2, 3, it could be 5 or 6 ultimately thermochemical equations, manipulate them to yield a target, add everything together, get an enthalpy of reaction. Well, instead we use tabulated delta HF values and we use their coefficients. So we multiply those values by the appropriate coefficient from the balanced equation, and so that ends up giving us enthalpies of formation for products and for reactants, and we use that in this simple equation: products minus reactants, where sigma is the sum of, so we add together the enthalpies of formation of the products and add together the enthalpy of formation of reactants. N is the stoichiometric molar equivalent. That's what you get for your balanced equation, and delta HF obviously is the enthalpy of formation for each compound. Now, one last thing I do want to draw your attention to is this. It's products minus reactants. Okay, this is a pretty common mistake. Pretty well everybody gets this right. Pretty well everybody remembers this equation. But you have to remember that the products are found on the right-hand side of the arrow. So these are the products, and so the products actually get listed first when you start adding things together. The mistake I've seen more than once is where people write down the correct equation and then they just start listing things from left to right, because that's how we're trained to read, and so they end up writing out reactants minus products, and so that would be incorrect. And the only thing that's, if you do all the math right, the only thing that's incorrect at the end of the question is the sign, but after all, that's still incorrect. So remember this equation and just be very careful when you get started using it. Okay, so here's a question. So we're going to use standard enthalpies of formation, and we're going to calculate delta H of reaction for this neutralization. So hydrochloric acid, or hydrogen chloride gas plus sodium hydroxide yields sodium chloride and water. Now that's balanced as written, so that's useful. And so we can just get started, start right in with the solving the problem. And so there's our equation, and then we're going to start listing our standard enthalpies of formation, starting with our product. So I've gone ahead and already looked these up. So what we have here is negative 411 kilojoules. has an enthalpy formation for sodium chloride plus enthalpy of formation of water in the liquid state is negative 286 kilojoules. Okay, so so we add those together. That's what the sigma means. We're going to add those together, and there's our products minus. We're going to do the same with our reactants. And so hydrogen chloride gas is negative 92 kilojoules enthalpy of formation. Whoops. Let's just get all of it in there. Negative 92 kilojoules plus, and the enthalpy of formation for sodium hydroxide is negative 427 kilojoules. Okay, so products minus reactants. Now we can go ahead and do the math. So negative 697 kilojoules minus negative 519 kilojoules, and we add that all up and we get negative 178 kilojoules. And so that is exothermic because delta H is negative. Now, just a couple of things to bring your attention to. So again, I wrote out this line. Okay, so everything's there. Enthalpy of formation for a single reactant, the other reactant, a single product, the other product. I wrote down all the values. Now, some people will actually take it a step further and write out everything in here just as, for example, I'll just show you, delta HF naught for, in this case, NaCl plus delta HF naught H2O liquid. And you can choose to do that if you want, but it's not necessary. But you do have to show the numbers. Okay, so in this case, you can start with a straight substitution if you want, but you just have to be really careful. And the last thing I wanted to show you was this, and again, just be careful with that. It's always products minus reactants, so there's the negative sign, that's always there. But in many cases, you end up with a negative value for delta HF of reactants. So don't forget minus, and a minus is a plus. That's why this is negative 178, not negative 1100 and something. Okay, so again, it's all about being careful when you do this. Let's look at another one. So here's a second one, standard enthalpies of formation for the combustion of, well, what's that organic reactant? That is ethanol, or methanol. And so we would hopefully realize that's not balanced. So we're going to go ahead and balance this. And when we balance it, it becomes, we're going to balance the carbons first. So one carbon, whoop, that's already balanced. Balance the hydrogen next. I have 4 hydrogens, so that makes it 4 hydrogen, make it 2 water. Balance the oxygens, 4 and 4. Now, I'm not a huge fan of those fractional coefficients for this. It just means multiplying by a fraction, which is not hard, and you can leave it like that if you want, or you can simplify it. So there it is, simplified. And so I've just multiplied everything by 2. Now I can apply my Hess's law equation. So there's the equation, and I've sped this one up a little bit by doing a bit of pre-work, but here's what we do. Substitution. So there's where I've written it out, 4 times enthalpy of water. Now notice here, what's new? It's this bit. So this is where the N comes in, and this N is right here, right? Sigma N, the molar equivalent of water. So there's 4 times delta HF of water, 2 times delta HF of CO2, etc. Now, also, why do I only have one term here? Well, that's elemental oxygen. Delta HF naught equals what? Well, it equals 0. So that's why there's no oxygen down there. It's not going to change the answer. All right, so now I can carry on and do some math. So there's the substitution of the numbers. There's the math, and again, negative, and that's a plus, right? Minus and a minus, so it's going to be add to it, and when I do, we get negative 1454 kilojoules. So the enthalpy formation, enthalpy reaction for the combustion of methanol, negative 1454 kilojoules. Makes sense. We'd expect the combustion reaction to be exothermic. One last one, combustion of urea. So combustion of urea, there's the formula, and oxygen, the products are nitrogen gas, carbon dioxide, and water vapor. Delta H of reaction is negative 633 kilojoules. What is the standard enthalpy of formation, delta HF, of urea? So what we're looking for here is delta HF of this particular compound. We are given the enthalpy of reaction. That's what we were finding in the previous two questions. Now we're given that. So the first step here, though, is to come up with our equation. So in the combustion of urea, CO, NH2, and that's actually a solid under standard conditions, plus oxygen, it is a combustion reaction, yields, and it tells us what our products are. Nitrogen gas, that's N2, plus carbon dioxide, that's CO2, and that's a gas, plus water vapor, H2O gas. All right, so there's our equation. We have to balance it. So carbons are balanced. Oxygen, well, that's going to change probably because I have 3 and I have, well, no, actually oxygen's balanced. Nitrogen, I have 2 nitrogen, it's balanced. The only thing that's not balanced, the hydrogen, so I'm going to balance that. So that's going to be, I'm just make a bit more room here. That's going to, I'm going to make that 2 waters. So now I've balanced the hydrogen, but notice I've changed the balance of the oxygen. And so I've made it CO2, that's 4 oxygens, and I have only 3 on here. So I'm going to make that, if I make that 3 halves, O2, I now have 4. I don't want to change this because then I change nitrogen and hydrogen and oxygen again. So that balances it. So that's the balanced equation. And I'm actually going to leave that coefficient 3 halves, and you'll see why in a minute. That's the equation to calculate the delta H of reaction, but we already have the delta H of reaction. We know this. What we're looking for is something in here. We're looking for a delta HF of, sorry, something in here, one of the reactants, the urea. So what we can go ahead and do is I would start filling this in. So delta HF of our products, delta HF naught of CO2 plus delta HF naught of H2O gas times 2, because there's 2 moles of it. And I can leave the nitrogen off. There is the delta HF of nitrogen, that's elemental nitrogen, is 0, so I'm finished with that. Minus delta HF naught of urea, CO, NH2, and that's all I have there because I also have the elemental oxygen, 3.5 moles of it. That's why you don't need to worry about converting that fractional coefficient. And now I can do this is where I would do a rearrangement. What I'm looking for is that delta HF naught of urea. So delta HF naught of urea, I'm just going to write it so a little quicker, equals. So I'm bringing that over the other side, so that makes it positive. There it is, positive. I'm going to have to get rid of this, so I'm going to minus delta H of reaction. So what I get is delta HF, I'm going to just keep going. Delta HF naught of CO2 gas plus delta HF naught H2O gas times 2. And so there's my product still, minus delta H of reaction, which I already know. And so now I can go ahead and do a substitution. It's negative 393.5 kilojoules plus negative 484 kilojoules. That's the delta HF naught of water vapor, which is 242 times 2, minus the enthalpy of reaction, negative 633 kilojoules. And so I solve that, I get a negative 877.5 kilojoules plus 633 kilojoules, and that equals negative 244.5 kilojoules. So the enthalpy of formation of urea is negative 244.5 kilojoules per mole. And so that's a couple of different ways you're going to use these enthalpies of formation. And so this is something you want to have some practice with. And that concludes this video.